So let me record. Now, as I said, this is going to be unsaturated hydrocarbons. Anytime you have a question along the way, please feel free to jump in, either asking me a question verbally or in the chat. All right, but let's talk about carbons. So unsaturated hydrocarbons, well, actually, let's take a step back. When I say unsaturated hydrocarbons, what does that mean? We've talked about saturated hydrocarbons, alkanes, but what does unsaturated mean? Anybody know? Well, remember when we say something is saturated in terms of hydrocarbons, remember every carbon has the maximum number of hydrogens attached to it. So it's either 3 or 4, one of the two, or sometimes it's 2. But again, it's the maximum number of hydrogens. So when something is unsaturated, it simply means it has more bonds and it's not fully saturated with hydrogens. And those two types are alkenes and alkynes. And we touched on this in the very first lecture when we introduced organic molecules, but we're going to dive much more in depth into these two compounds because you'll see later on in the lecture they do have some chemical and medical importance. So they can be, and not just that, just like average everyday life importance as well. So interesting group of molecules. Now, alkenes are carbon compounds that contain carbon-carbon double bonds. So this would be an example of an alkene. Now, as we talked about last week and the week before, when something is an alkane, right, it doesn't have any double bonds going on. But if we had an alkane like this that was, C2H6, it would be ethane, right? Now, when with our alkenes, we drop the ane and we substitute an ene, E-N-E. So this is ethylene. Fun fact about ethylene. Ethylene is a gas produced by plants. It's produced by many things, but it's produced by plants to help plants ripen. So fruits, apples, oranges, things like that ripen because of ethylene gas. Fun fact. Now this double bond creates our trigonal planar equal 120-degree bond angles between all atoms associated with a double bond in one of these alkenes. And there is a generalized formula for alkenes. It's CnH2n. And remember, N is simply the number of carbons. So in this case, we have ethylene. It's C2H4 because we do 2 times 2 gives us 4. So C2H4. That's our generalized formula. Now, alkynes, replacing the alkanes with wynes, are compounds that contain a triple bond. Now, triple bonds are not that common. They're really not. They're particularly rare things in nature. They're hard to form. They're really hard to break as well. They're the strong, as we discussed in Principles of Chemistry 1. Triple bonds are the strongest you get in terms of bonds. But now an alkyne has a triple CC bond. Now structurally, it has, because of the triple bond, it has exactly 180-degree angles between bonds here, as you see in this figure. And alkynes have their generalized formula CN H2N minus 2. So in this case, we have acetylene, which is C2. So it'd be C2H, then 2 times 2 is 4, minus 2 is 2. So it's C2H2 for acetylene. Fun fact about acetylene, it's commonly used as a fuel. So if you've ever seen like really hot burning torches in like metallurgy or something like that, they're acetylene torches. They're kind of burn really hot. They burn like thousands of degrees. It's kind of cool. So now, very much like alkanes, our alkenes and alkynes are composed of nonpolar bonds, and their physical properties mimic that of those of alkanes. Now, and this will become clear what that means in a second, but alkenes and alkynes have a lower melting and boiling points, and like alkanes, are insoluble in water. And as I sort of discussed at the very start of this little talk, they're unsaturated because they contain fewer than the maximum number of hydrogen atoms per carbon. So they contain less than 3, right? That's what we're getting at there. Now we can draw these, but we always need to make sure when we're drawing an alkene and an alkyne that we have the multiple bonds. They're always drawn in our condensed structure. So if we have ethylene, well, something that resembles ethylene, we have to draw this like this, so CH3, CH, and then double bond. Now it looks like the double bonds between the carbon and the hydrogen here, but it's just It's just accepted that it's between the carbon and carbon, just as a note. So just to let you know, remember, because hydrogen can't double bond, right? It can only do one bond. And then the same thing here when we have a triple bond. Again, we have to keep the triple bond, but we get rid of the single bonds as well. So just a slightly different variation of what we did for alkanes. We just have to show those double and triple bonds. So let's talk about how we name these suckers, because that's part of this course, right? We got to talk about how we use IUPAC to name things. So we'll start off with these two compounds, A and B. These are their chemical formulas. They're not too different. We have an alkene and an alkyne. Now, very much like we did with alkanes, we have to find the longest chain, but however, this longest chain has to incorporate that double or triple bond. So in this case, we have this alkene here, so 1C, 2C, 3C, 4C, that's the longest chain. Technically, we could also go 1C, 2C, 3C, 4C. They would be functionally equivalent, right? Because they both have a methyl group coming off the same place. So it doesn't really matter which one you do. But it's the longest chain is 4. And then for our alkyne, 1, 2, 3, 4, 5, 6 would be our longest chain here. Again, we could go 1, 2, 3, 4, 5. But again, that's still too short, right? And it doesn't include the triple bond. So our alkenes and our alkynes, remember, it has to include that triple or double bond. Now, once we identify the longest chain, 4 carbons and 6 carbons, we have to match that to our names, right? We know methane is 1 carbon, butane is 2 carbons, ethane is, and so on and so forth, right? All the way up to technically infinity, but you know, that's that nomenclature we have to use. Now, 1, 2, 3, 4 carbons is butane, but there's a double bond, so we have to change the ane to ene, so it's butene, right? So remember, if this didn't have a double bond, it would just be butane, right? But it's butene because it tells us there's a double bond present. And the same thing here. We have 1, 2, 3, 4, 5, 6 carbons. That's hex, but instead of hexane, it's hexyne, which I think is a weird one to say, but hexyne. And then we do very much like we do for the other ones, right? We start numbering, right? We number the carbon chain from the end that gives the lowest multiple bond, the lower number. Same exact thing for alkanes. So 1, 2, 3, 4 here, right? But we're trying to give the multiple bond the lower number, right? So we don't go 1, 2, 3, 4, even though this would give the substituent, right, this R group the lowest number. We have to give the double bond the lower number. So we have to go left to right here, not right to left. So it's slightly different, but not, again, not all that different, right? We're just trying to, instead of give the first substituent its lowest number, we're just trying to give the double bond or the triple bond its lowest number. Now the same thing here, 1, 2, 3, 4, 1, 2, 3, 4, right? So we have to go this way because it gives the triple bond the lowest number. Because even if we go this way, right, 1, 2, 3, that would give the ethyl group here the lowest number, but it doesn't give our friend here, right? It doesn't give our triple bond the lowest numbers. Now, once we get those numbering systems down, we name the compound using the first number assigned to the multiple bond. Now, why do we do that? We want to tell the person that reads this name that where is that double bond or triple bond located. So in this case, we have CC bond, it's on the first carbon here. So we have butene because we have 4 carbons. It's Snickers, stop. We have, sorry, puppies are barking. We have butene, it's between the 1 and the 2 carbons. So it gives butene its lowest number, which is 1. So it's 1 butene, telling us that we have butane, but the double bond is between the 1 and the 2 carbon. Same thing with hexyne here. We know the triple bond is at the 1, 2 carbon, so it's 2 hexyne. So again, slightly different for our alkanes, because we have to denote first where that double or triple bond is. Then finally, we have to look at the substituents, right? We have to look at those R groups. So in this case, we have a methyl group on our butene, right? And we number this 1, 2, 3. We see that methyl group as at the 3 spot. So thus we started with 1 butene. We add the 3 dash methyl dash 1 dash butene. So let's break that apart. It says, okay, I have butene, so that means I have a 4-carbon member. The ene tells me I have a double bond, and that 1 tells me that double bond is after the first carbon. So again, what this 1-butene tells me is this part in the box. And then as we saw with the alkanes, the 3-methyl part just tells us I have a methyl group coming off the 3 spot. So again, it's a logical flow of how to name these things, but again, slightly different rules. Now let's look at the hexyne. So again, the 2-hexyne part, hex telling me I have a 6-carbon chain, yne telling me there's a triple bond, I have an alkyne, and the 2 tell me that triple bond is after the 2nd carbon. So remember, 2-hexyne just tells me what's in this box. And then I have a group at number 4. It's 2 carbons long, so that's an ethyl group, right? Meth, eth. And it's at the 4 spot. So I have at the 4 spot, I have an ethyl group. So putting it all together, I have 4-ethyl 2-hexyne. And that's how we do it, right? It's not different, right? It's not at all different from what we saw. But again, we have to take into account 2 key things. First, changing the ane of an alkane to an yne or an ene, and then just having a number telling the person who's reading this IUPAC name what carbon the double or triple bond comes after. And that's it. And I think, again, these rules are all really nice and sort of straightforward, but again, it's about applying sort of a logical flow of, okay, let me number this. It has to be the longest chain, blah, 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 and then I go from there. So it's kind of this, this logical flow. Now, compounds can have double bonds. And so when a compound has 2 double bonds, they're called dienes, as you would imagine. Enes being, the alkene, and di meaning 2. All right, so when we had dimethyl, we know we had 2 methyl groups. Now, dienes are named by changing the ane part of an alkane to a diene, which is kind of a weird way of saying it, but that's what we're getting at. So each double bond does get its own number. And so we have this molecule here and here. So let's just break down these 2 molecules. So we have bute, because we have a 1, 2, 3, 4 carbon chain. So butane is 4 carbons. Now we have a diene, because we see I have 1, 2 double bonds. So butadiene tells the reader bute 4 carbons, di 2, ene double bonds. So I have 2 double bonds. And now I just have to say, okay, what carbon do those double bonds come after? Well, in this case, it doesn't actually matter which order I number. Now, in this example, I've gone 1, 2, 3, 4. Actually, if I went the opposite way, it's equally as okay. 1, 2, 3, 4 produces the same result, which is nice. So in this case, I have, what I'm telling you is that the 1 spot here and the 3 spot here, I have a double bond. So 1, 3, butadiene. Again, the diene telling me I have 2 double bonds, and the 1, 3 telling me the first one's at the 1 and the second one's at the 3. So again, exact same as we just discussed, but again, just getting slightly more complex with the diene part. Now we can look at this much more complex example. The largest carbon chain, 1, 2, 3, 4, 5, 6. So it's got to be hex. I see I have 2 double bonds, so that means I have to change diene. I have to add diene to hex. So I have hexadiene, and I have to start numbering. So 1, 2, 3, 4, 5, 6. So that's great. If I went this way, 1, 2 would put my lowest number at actually 2. So remember, I have to go this way because my lowest number has to be the first double bond, right? Or one of my lowest numbers needs to be that first bond. So in this case, I have a double bond at 1, 2, 3, 4. I have a double bond at 4. So 1, 4 hexadiene. Again, hex 6 carbon chain. Diene, I have 2 double bonds, and the 1, 4 tells me at carbon number 1 and carbon number 4, that's where that diene, that double bonds have to be. And then finally, I have a methyl group coming off the carbon number 5. So 5-methyl 1, 4 hexadiene. So again, it's just about applying layers. It's like making a sandwich almost. Not a sandwich you'd want to eat, but it's like making a sandwich, right? Just applying layers, right? The hex is 6. A diene, 2 bonds. 1,4, that's where the bonds are. 5-methyl, I have a methyl group at the 5 spot. And that's my IUPAC sandwich. Again, not a sandwich you want to eat, but it is a certainly a sandwich, right? You're building layers, right? It's like an onion. You're just getting layers on top of layers on top of layers. Now, and I'll just make note, if you had diene or triene or tetraene, you could do that as well, just as a note. Diene just implies 2, right? If you had triene, it'd be 3. Tetraene, it'd be 4, right? So just as a note, you can go beyond just the 2. Now, when we have cyclic rings, so when we have cycloalkanes, right, they can also have double bonds, as you see from these 2 examples down below. Now, the double bond, like we did with straight chain alkenes, has to be the lowest number as well. So in this case, I have to put that double bond between the first and the second carbon. So when I go through and name these 1 through 5 and 1 through 6, that double bond should be the lowest number possible. And then the ring is also numbered to give the first substituent, or that first R group, its low number as well. But again, you have to make sure that double bond is between 1 and 2, and you try to get that substituent also a low number as well. So when we look at this first one, it's a ring, so it's cyclo, right? So that's what the cyclo part. Pent, 1, 2, 3, 4, 5 carbons, so that's the 5 carbon pent. And then we have tene, or ene, I should say. That tells us that it's an alkene, right? It has that double bond. Now, that double bond always is in the lowest number. So in this case, we actually don't put a number to note where it is. It's just always assumed in cyclic compounds that they are at the lowest number. So it's between 1 and 2. That is if you only have 1 double bond. We'll get to examples where we have 2 double bonds. Well, not today, but in class Wednesday, where we have some special naming to go through. But for today, we're just thinking about it's always between 1 and 2. And then, so cyclopentene, that tells us it's a ring with a double bond between the 1 and 2 spot. And then we have a methyl group, and it's at the 1 spot, so it's 1-methyl. Now, the slightly more complex example, again, we have 2 substituents here. We have 2 methyl groups here. But we have 1, 2, 3, 4, 5, 6. So it's a 6-member carbon ring. So it gets the cyclo and the hex part. And then the ene, because we see there's a double bond. Now we notice we have 2 substituents here. We want to make sure at least we want to get those substituents as low numbers as we physically can. But remember, the double bond has to go between carbon 1 and carbon 2. So we have to label this carbon 1, carbon 2, all the way around to carbon 6. So we break that apart. We have a methyl group at carbon 1, a methyl group at carbon 6. Thus, we have 1,6 dimethyl, because remember, I have 2 methyl groups here, cyclohexene. So again, not too different from naming normal alkenes. Normal cyclic compounds. But again, we have to make sure that double bond is between our two lowest numbers as best we can. Now, we could technically have multiple double bonds. We could have a double bond here and a double bond here, but we just have to make sure that double bonds get the lowest numbers we can physically get. That's all. So, now, one of the cool things about our enes, our alkenes, there we go, is they actually have restricted rotation. And so when you have a double bond, it produces some really limited numbers of shapes you can take. This is what we call restricted rotation. And these 2 restricted and distinct shapes are what we call the cis and the trans isomers. Now, it's the trans might sound familiar, right? You might have heard of like trans fatty acids, and this is why they're called trans fatty acids. But it really just refers to what side of the double bond are your substituents on, or your R groups. Now, if I have 2 butene here, right, butene being 4 carbons, right, ene double bond, and then 2 is because the double bond is between the second and the third carbon. Now, with that shape, butene has 2 potential arrangements. Now, we take butene and we can either write it like this, where we put the two methyl groups here on the same side, i.e. north, or north or south, whichever one. And when they're on the same side like this, right? So you think of this kind of like there's a invisible barrier here, right? When they're on the top of the invisible barrier together, they're in what we call cis formation, or they're isomers, right? Isomers are just the same chemical formula, slightly different shapes. So they're both on the same side of this sort of this axis of this molecule. And when they're in a trans formation, as you can see, they're just on the opposite. So we just have this, again, this invisible line right down the middle of the carbons. They're simply on opposite sides of one another, as opposed to being on both the same side. So cis and trans isomers give us distinct shapes. And you have to account for that when you're drawing and naming things. And we'll get to that in just a moment. But again, same chemical formula, slightly different shape. And you could reason, if I'm giving these special names, cis and trans, that they probably have distinct properties. And you would be absolutely right. A cis and a trans are different in their behavior. So just as a note. But when we write this, again, same chemical formula, 2-butene, but they have two different names. They're two different compounds, and they have two distinct sets of properties. Now this one, with the two methyl groups on the same side, so cis is labeled cis. Doesn't have to be italicized when you're writing it up by hand, but cis-2-butene. And this one, because the carbons are on the opposite sides, trans-2-butene. So again, different compounds. If I just wrote 2-butene, you wouldn't know which one it was. But if I write cis-2-butene or trans-2-butene, you know specifically they have to, again, on that double axis, they have to take, the double bond axis have to take different shapes. So this one, they kind of got to look like a poodle. That's what I've always seen this look like. And I don't have a good name for this one. Maybe like a seahorse. But that's the sort of the distinct of a cis and trans isomers. Again, same exact chemical formula, different IUPAC names, different shapes. And as we've discussed, shapes dictate function, right? Different shapes give these chemicals different properties. Now, whenever two groups on the end of a CC bond are different from one another, there are two isomers possible. So in this case, these two groups must be different from one another for there to be a distinct possibility. And these two groups also must be different. Now, what do I mean by that? Well, let's go back here. This is different from this. This is different from this. Thus, there are two isomers. However, if this was CH3 and CH3 and CH3 and CH3, that's the same. Thus, there's no distinct isomers. So they have to be different. A has to be a methyl group and B has to be a hydrogen, or vice versa. And C has to be a methyl group and D has to be a hydrogen, right, or vice versa. So they have to be different. If they're the same, you don't get isomers. That's all. I think that makes intuitive sense when you kind of picture it, right? Now, when two of the groups on one end of the double bond are identical, so in this case, I have two hydrogens here, and then I have a ethyl group and a hydrogen here, there are no cis and trans isomers possible either. So in this case, I have hydrogens here, and I can write the methyl group, the ethyl group here or here, but this is exactly the same. Exactly the same. So you don't need to account for this at all. But again, if A and B are different and C and D are different, then you can have two distinct isomers. But when A or B is the same or C or D is the same and the other is different, again, there's no possible isomers here. So it's a good sort of rule of thumb to keep in mind, like what is required to have different isomers, right? And in case of cis-trans ones, right, it has to have two different substituents on both sides of the double bond. Now, a term we've already mentioned, but I'll just repeat it. It's what we call stereoisomers. And these are isomers that differ only in the 3D arrangement of atoms, which is in contrast to constitutional isomers that differ in the way the atoms are bonded to one another. So let's look at example. Now, our cis and trans, they fall under stereoisomers, and they have just slightly different 3D arrangements, right? Cis are on the both side, trans are on opposite sides. So those are going to be stereoisomers. All right? And there's cis-2-butene and trans-2-butene. Now, in contrast, we have constitutional isomers where cis-2-butene and trans-2-butene are different than 1-butene, right? So stereoisomers slightly differ in the 3D arrangement. Constitutional isomers differ in the way the atoms are bonded to one another. I don't think I need to point out how different this looks than this, right? Same butene, same chemical formula, different 3D shape, different bonding of molecules, right? This looks nothing like these two. That's why they're considered constitutional isomers. These ones just slightly differ in that 3D arrangement of atoms. So now you can imagine that even though they have the same chemical formula, they're going to have different properties, and they're going to have the same chemical formula, but different in very different 3D shapes, and all the other properties that are associated with alkenes and alkynes are also going to be different. Now, there are special types of hydrocarbons out there. Now, these are fatty acids. Now, you guys have probably heard of fatty acids before. They're the major component of cellular membranes and all sorts of other fun stuff medically. Now, fatty acids are carboxylic acids. Now, if you remember back from class 1, a carboxylic acid has the generalized formula RCOOH. And typically speaking, fatty acids have very long carbon chains that typically comprise 12 to 20 atoms long, carbon atoms long. They can be longer, they can be shorter, but typically speaking, they're 12 to 20. Now, they are naturally occurring. They're occurring in animals, they occur in vegetable oils, right? And vegetable oils are formed from fatty acids, so they are naturally occurring. Now, saturated fatty acids have no double bonds, as their name implies, whereas unsaturated fatty acids have one or more double bonds in their long hydrocarbon chains. So when you look at a food label and it says, you know, unsaturated fatty acid, or it says unsaturated fat or saturated fats, that's what it's getting at, right? The presence of double bonds. Now, generally speaking, double bonds in naturally occurring fatty acids are typically cis. Typically, right? They're typically on the same side. However, as the number of double bonds does increase, the fatty acid, as the number of double bonds in the fatty acid increases, the melting point also decreases. So it's kind of this weird function. As you increase the number of bonds, melting point decreases. Now, fats that are generally formed from fatty acids having few double bonds are solid at room temperature, right? So like butter, it's solid at solid-ish at room temperature. However, oils are generally formed from fatty acids, having a large number of double bonds and are thus liquid at room temperature. So you can think of something like olive oil, right? Olive oil has, it's liquid at room temperature, thus meaning it must have lots of double bonds. And so we could do two comparisons here, stearic acid and oleic acid. You've probably heard of oleic acid. It's pretty common in butter, but you can see there's one double bond here. So, but they're both in that cis formation, and then you have stearic acid, which is just a straightforward straight carbon chain. Now, there is an interesting fatty acid. Interesting hydrocarbon. Not fatty acid, hydrocarbon called lycopene, and many of you might have heard of lycopene before, but lycopene is the red pigment in tomatoes and watermelons as well. Tomatoes are fruits. That's why they have a similar pigment as watermelons, which are also fruits. Now, as you can see from this figure, lycopene has 13 double bonds. Now, lycopene serves some pretty interesting functions inside the human body. It's been shown to be an antioxidant, so it's a compound that prevents unwanted oxidation from redox reactions. So it helps protect you against yourself. And in terms of health-wise, it's also shown that diets that have high levels of antioxidants, such as lycopene, also result in decreased risk of heart disease and cancers. That's one of the things they implicate in heart disease and cancers are these oxidants. And lycopene's also been shown to be effective at treating testicular cancer. So those men with higher amounts of lycopene in their diet have lower incidence rates of testicular cancer. So kind of a double function there. Now tamoxifen is as you can see, it's an alkene, right? It's got double bonds. It's got some other stuff, but at its heart, it's a alkene. Now tamoxifen has been used in the treatment of breast cancers that require estrogen for growth. So there's many types of cancers out there that require our own body's hormones to grow. Breast cancer is one of them, or some breast cancers is one of them. There's a lot of different types of breast cancer. They're not just like one breast cancer, but there's some types of breast cancer out there that require estrogen, and tamoxifen actually helps protect your body from producing too much estrogen, which would then fuel those cancers. So tamoxifens, again, are great little alkenes that are used for treatment of breast cancer. Now, contraceptives also take advantage of alkenes. So we have synthetic birth controls, and the structure inside there are very similar to the sex hormones estradiol and progesterone, but they also contain CC triple bonds. So this is progesterone and estradiol. They're common female sex hormones, estrogen, right, or progesterone, right? This is what they look like. Now, our synthetic ones look like this. So these are alkynes, right? They triple bond, so they're alkynes. So we have ethyl nyl estradiol, I think I said that right, and noretherodrome. And you can see these similar structure to your natural, or at least for women, your natural body's hormones. And so these synthetic hormones contribute to the, again, similar structure, but contribute to your body. You're essentially, these medicines tricking your body into, being immune to getting pregnant. Well, partially immune to getting pregnant, of course. It's not 100% effective, right? So that's kind of fun. So again, cool medical applications, maybe applications to your everyday life. But, alkenes, alkynes, very much like alkanes, serve function in your average everyday life. Now, alkenes, they do react with things, so they're not biologically inert, and they typically undergo what we call addition reactions. You should, recall that from Principles of Chemistry 1, where you add some form of group, in this case it's designated XY, are added to the alkene. Now, what typically happens, one bond of the double bond is broken and two new single bonds are formed. And I think that's pretty straightforward to see here, but we have some sort of alkene here. We can see because we have the double bond, it reacts with XY, which is some compound, and it produces, getting rid of that double bond and producing two single bonds here, where we attach XY to our alkene. Now, there are a number of different types of reactions, and I'll just discuss them just briefly. So we have this hypothetical compound, cyclohexene. Now, under the presence of a metal catalyst, cyclohexene can react with hydrogen gas, so H2, to do what we call hydrogenation or hydrogenation. And basically, we strip the double bond away and add hydrogens in. So if you've ever heard of like hydrogenated oils, it's done by a hydrogenation process, just as a note. Now we can halogenate cyclohexene here by reacting it with chlorine or bromine, attaching two chlorines or two bromines onto our ring. We can hydrohalogenate it. So if we have HX, so HCl or HBr, so an acid, hydrochloric acid or hydrobromic acid. We're actually going to do this in lab, just as a note. We can hydrohalogenate them, so attach a hydrogen and the halogen, aptly named hydrohalogenation, and then we can react it with water in the presence of hydrogen sulfide. Sulfuric acid, so H2SO4, and adding both a hydrogen and a hydroxyl group to our ring, thus calling it a hydration reaction. Now, why is it called a hydration reaction? Well, we're adding HOH, and that's just water. So we're adding a full water molecule to our hexene ring, which I think is cool, right? So these are the four most common ones. We're going to do we're going to do hydrogenation and hydration in lab, if I'm not mistaken. Yes. And so you'll get to see what this is like in person. It's not exactly the most exciting thing in the world. You just change it a little bit. So just as a note, chemistry is not always the most exciting thing, but you get to do it anyways. Now, as I mentioned, hydrogenation is the addition of hydrogen gas to an alkene. So this is what it looked like, right? Alkene plus hydrogen gas over a metal catalyst. Now, the metal catalyst, if you sort of remember what catalyst does, right? A catalyst simply lowers the activation energy for a reaction to occur. So if this reaction is going to occur, it would happen at some rate independent of the catalyst, right? And that's all dependent by energy, right? Movement of molecules and all that fun stuff. Now, the metal catalyst, it's kind of interesting what it does. It speeds up the rate of reaction by actually physically forcing the alkene and the hydrogen to interact in physical space with one another, thus speeding up the reaction, which is, I think, is a pretty cool thing. In our case, it's usually palladium, PD. It's usually the most common thing. And then when you hydrogenate something, the output obviously is an alkane, right? I went from an alkene, I got rid of the double bond, I only added hydrogens, thus I am back to an alkane. So kind of fun. And as I mentioned, the metal catalyst provides a surface that attracts both the alkene and hydrogen, which helps the reaction, right? Remember, what determines a reaction is a couple things, right? But one of the most important things is, do the molecules physically touch, and do they touch in the right orientation? And if they don't do one of those, the reaction simply doesn't occur. But by having palladium present, it forces them into the same spot, interact properly. So I think that's kind of a conceptually important thing. Now, halogenation, as we mentioned, is when we add a halogen, bromine or chlorine gas to an alkene, producing a dihalide. Now, halogenation doesn't, as you can see, requires no catalyst, and we do have a dihalide. A di meaning two, halide just meaning a halogen. Right? Remember, halogens are column 7 in the periodic table, right? So they have 7 valence electrons. They only bind once, right? They have very high electronegativity, right? Group 7A, if you need a refresher about what it's called. I'm sorry, about their properties. But this is our halogenation. We're producing a dihalide, and this looks a little bit like this. So we had ethene and cyclohexene. They react with chlorine or bromine, thus producing a dihalogen having 2 halogens on them. Hydrohalogenation is when we had an acid, so hydrobromic acid or hydrochloric acid, so HBr and HCl, and we stick them on. And we're sticking both hydrogen and the halogen. Now, what we've attached now is an alkyl halide. So new term. Well, no, not technically a new term, but refreshing your memory on a term we heard in the first class, an alkyl halide. HX, alkyl halide. And this is what we have here. We have ethene and cyclohexene. They react with hydrochloric acid and hydrobromic acid, producing chloroethane. So you can see we've gone back to the alkane here. The chloro telling us we have a chlorine present. Bromo cyclohexane. So we went from hexene to hexane because again we got rid of the double bond. Bromo telling us we have a bromine attached. Excuse me. Chemistry is totally not boring or anything like that. Now, there's a couple interesting properties here. Now, if the reactant itself is an asymmetrical alkene, 2 possible products can be formed in theory. Now, what does asymmetrical mean? Well, remember, on both sides of this double bond. Now, this is asymmetrical, right? Now, if we have this hydrohalogenation reaction here, reacting this propene with hydrochloric acid, we could produce 2 distinct compounds. That chlorine can attach to this carbon, or it can attach to this carbon. So C1 or C2, it doesn't matter. But they produce 2 distinct compounds, 2 chloropropane or 1 chloropropane. Different, right? So different, they're going to be our constitutional isomers, right? They're going to differ in the arrangement and attachment of atoms. So you have 2 potential avenues here, 2 chloro or 1 chloropropane. But again, either way, we're getting rid of the double bond. Now, we're going to introduce a brand new rule. It's not like a cool law or anything like that, but it's a rule. It's called Markovnikov's. Markovnikov's. There we go, Markovnikov's. Russian names are hard to say, okay? Now, his rule states that the hydrogen atoms of an HX bond will bind to the less substituted carbon atom in the CC double bond. So in this situation, this chlorine will bind to the less bound one. So this means that the carbon in this the carbon in the double bond with the most hydrogens will bond to the hydrogen atom of the HX. So what does that physically look like? Well, we have propene reacts with hydrochloric acid, so we have this reaction. Now, we examine which one has the most hydrogens, right? Well, we see this one has 2 hydrogens, this one has 1 hydrogens. Now, his rule states it will bind to the less substituted carbon atom, so it has the most hydrogens. So we say, which one has the most hydrogens? This one has 2, this one has 1, thus the hydrogen has to bind here, and the chlorine has to bind there. So there's only one potential product here, right? I said in the previous slide there might be 2, but based on this rule, the hydrogen has to bind here, and the chlorine has to bind there. It's a binding rule. It's not like a law in the sense that it always occurs, but in terms of this class, it's a binding rule. So anytime you're trying to halogenate something, or I should say hydrohalogenate something, the chlorine always binds to the lowest number of hydrogen-containing carbons. And again, this is just another example. This carbon has 1. This is the example we were just working on, but it's just color-coded for your sake. So again, telling us looking for the lowest number of hydrogens for the chlorine to, in fact, bind to. Now, our final one, hydration, is the addition of a water to an alkene. And again, this is in the presence of a strong acid. In this case, we're looking at sulfuric acid, H2SO4. So we react this alkene to water, HOH, right, H2O, and it produces an alcohol. So by having hydrogen sulfuric acid, so the strong acid present, when we react water with our alkene, we actually attach a hydrogen and a hydroxyl group, thus making this an alcohol. So remember, anytime you see an OH, it's an alcohol. So when we looked at the estrogen and stuff like that, those were alcohols because they had an OH present. So let's look at this this exact reaction that was here, but this is what we're going for, right? We're tacking on the H and the OH. Now, there is a rule here as well that we need to take into account. Now, if the reactant is asymmetrical, so remember, asymmetrical, same thing on both sides, right? Or different things on both sides. The product rule will be determined by our friend Mark Anovic. I don't know. I'm not going to try again. I'm going to stop trying to say his name. About our friend's rule here. So this carbon has 1 hydrogen bond, so the OH has to bind here. The carbon has 2 hydrogen bonds, thus the H has to bind there. So when we react it with water and sulfuric acid, the hydroxyl group has to bind here, and the hydrogen has to bind here. So exactly the same, looking for the number of hydrogens. And again, there's only one possible outcome here, and it has to be this, not the other way around. All right, so let's talk about butter, because everyone likes butter, and if you don't like butter, you're lying, because butter is the best. Now, butter is made up of saturated fatty acids, and you can see it's saturated, right? All the CC bonds are single bonds, right? There's no double. I mean, there's a double bond here, but that's a different functional group, right? So the main fatty acid chain here is all single carbon bonds. Now, a diet that's rich in saturated fatty acids, so saturated, i.e. butter, is considered typically to be unhealthy. You want more unsaturated fatty acids. And so people have tried to, and I should say people, scientists have tried to produce alternative versions of butter or margarine with similar taste and properties, but with more, or at least one, C to C double bonds. That is making them unsaturated fatty acid change. Now, it's kind of interesting. Now, part of the reason why double bonds are better is because when they're kind of going through you, they're good at scraping. Whereas where saturated ones are stickier and they like to stick to things like your arteries. So that's kind of part of it. Sticky versus non-sticky. But that being said, most naturally occurring unsaturated fatty acids are liquids at room temperature. So oils, things like that. However, to make the desired butter alternative, i.e. butter with double bonds, we actually have to add a compound that is solid at room temperatures. So what we do to make butter alternatives like margarine, we partially hydrogenate them, so we stick on hydrogen, right, to unsaturated fatty acid compounds. So this process allows for a few CC double bonds to remain on the chain, but it adds enough single bonds back in to make them solid at room temperature. So this partial hydrogenation is what makes margarine, which is theoretically healthier than regular butter, though less tasty, be solid at room temperature, where all indications tell you because it has double bonds, it should be liquid at room temperature. So we can just look at this. We have unsaturated vegetable oil. You can see there's multiple double bonds here, thus it's liquid at room temperature. Right? Low melting point, liquid at room temperature. High boiling points though, right? Remember that's a characteristic of our hydrocarbons. Now we have Benecol, which is a butter alternative. Not terribly tasting. I don't mind Benecol. I've tried it before. It's not too bad. Now we've partially hydrogenated. Now you can look at the structural similarity, right? It's very, very similar. Now we can partially hydrogenate oil that's typically healthy with hydrogen, right? Hydrogen gas, to add hydrogens to 1 CC double bond, as you can see here, right? So the CC double bond now has hydrogens tacked on. So thus removing a double bond, making it solid at room temperature, but there's still one double bond present, thus making this healthier than regular garden variety butter. So kind of an interesting thing if you like butter or if you like butter substitutes. I think both are good. They both have they have their ups and downs. So that's fun. Now partial hydrogenations sometimes leave trans double bonds on the fatty acid. Remember, most fatty acids have cis double bonds, right? As you can see here, right? Cis double bond, cis double bond. However, sometimes hydrogenating things adds trans fatty acids. So remember, across. Now, trans fats, as I'm sure you guys know, are actually outlawed in some places in the United States and Europe. But trans fats are actually widely considered to be unhealthy or sometimes more unhealthy than saturated fatty acids. It's kind of up to debate depending on who you ask. But we do know that saturated and trans fats are not exactly the best for you. You want to go for more unsaturated ones. But nutritionists do agree that a healthy diet consists of very few saturated or trans fats. And you can see what this looks like, right? So we have a trans fat, again, similar 3D structure, right? Right. The difference between a saturated and a trans fatty, look at that, it's almost identical. But you'll notice that the trans one, right, again, on this double bond, they're diagonally across from one another, thus making it trans. So structurally, a trans fatty acid actually has a very similar structure to a saturated fatty acid, which is why I think they're equally as bad for you. Though some people do argue that trans fatty acids are worse for you. But I don't know enough about this issue to weigh in on it, but you can figure it out by Googling. I'm sure there are people that think about this more than I do. So next up, kind of interesting thing, which is we call polymers. Now, polymers, for those of you that have taken biology, will sound pretty familiar. But polymers are simply large molecules made up of repeating units of smaller molecules, or monomers, that are covalently bonded together. So we can look at an example of this. We have ethylene monomers, and the individual unit here is an ethylene. So we have ethylene, ethylene, ethylene. Now we polymerize them, getting rid of double bonds, but joining all of our ethylenes together. So we have this polymer ethylene. Kind of cool, right? And we're joining 3 to make 1. So we have a polymer, which is multiple units of monomers strung together. So if you think about this, like from a biology standpoint, it's like sugars, right? Polysaccharides are multiple sugars joined together. A monosaccharide is just a single sugar. Now, as I mentioned, in polymerization, the double-double bond, the CC double bonds are broken, and single bonds linking the monomers are then formed. So we have CH2 bounded to cheese. No, I'm just kidding. It's not cheese, but like cheese is written like CHG, so I would associate this with cheese. But CH2 bound to CH, then something. The Z C just represents anything. We link those together, right? We get rid of those double bonds in favor of single bonds, and we have this repeating unit of CH2 CH bound to Z to the end. So it could be any number, right? If I had 100 of them, it would just the n would be substituted with 100. So this is our shorthand for polymers, right? CH2 CH bound to Z, and then that's in brackets with a subscript n, which tells us it could be any number from 0 to infinity. Not negatives, or I say 1 to infinity, not 0. But polymers are important. Now, there's a couple ones you've probably heard of, and others you probably have never heard of at all, but you use them all the time. So PVC, polyvinyl chloride, is a repeating unit, right? CH2, CHCl. So PVC, something your water and your pees and your poops flows through every day. Really important type of piping for modern building. Polyacryl nitrile. There we go. CH2, CHCN. Common fiber, plastic fiber of clothing. Now, you might not realize this. A lot of your clothes contain plastic fibers. You might say they're cotton, but they do contain, a lot of times, plastic fibers to help hold them together. Polyisobutylene, if you ever use like a ball, repeating monomer of CH2, C, CH3, CH3, creating balls like this, not basketballs, but like rubber balls, like if you play dodgeball, that type of ball. And then polystyrene, which is, you guys know, mostly a styrofoam, but it's CH2, CH, and then a hexene ring here. And so that's polystyrene, one of our plastics. But you'll notice these are all some derivative of plastic, right? These polymers come together to form plastics, which are really important for our society, right? Not just for beaming each other with these, but clearly really important for the functioning of our society. Right? Plastics are super important. They shouldn't be, but they are. But I won't go into how much I don't like plastics. For those of you that take biology 2 with me this semester, you'll have to listen to me tell you how much I don't like plastics in like at the end of the semester. But not now, not today. Now, we have a special class of alkenes, which we call aromatic compounds. Now, aromatic compounds are compounds that contain a benzene ring. Now, benzene ring should sound familiar, right? A benzene ring has a standard chemical formula, C6H6, 2 double bonds present, right? This is a standard chemical formula for a benzene ring. Now, each C is trigonal planar, so each one has a 120-degree bond angle. Thus, benzene is a planar molecule. It's essentially flat, which is actually kind of cool. Now, aromatic carbons are interesting compounds, and we'll talk about what they do for you in a second. But chemistry speaking, each of these representations, as we see here, is actually the same arrangement of atoms, but different locations of electrons. So in a benzene ring, you can kind of rotate things, and kind of rotate where they are. Same chemical formula, same overall structure, but slightly different arrangement of atoms. And electrons as well, obviously. Now, these are what we call resonance structures. So in this case, actually, neither of them is actually the true structure of benzene, which is kind of a weird concept. if this isn't the correct structure of benzene and this is the correct structure of benzene, what is the actual correct structure of benzene? And the reality is the actual structure of benzene is a hybrid. It's both at the same exact time. Now, you can think about this conceptually as they both exist at the same time, or they swap back and forth, right? Kind of like, for those of you that have ever heard of Schrodinger, Erling Schrodinger and his cat hypothesis, right? That's that idea, right? It's one or the other, but sometimes exactly the same, right? So they kind of either flop back and forth or both exist simultaneously at the exact same time. Now, in this structure, all three electron pairs in the double ring bonds are what we call delocalized in the six membrane ring. So, thus, we can draw benzene rings as one of three things. We either draw it like this, with this arrangement of double bonds, or this arrangement of double bonds, or we just draw it like this. Either is technically correct, because remember, it's essentially a it's essentially like both occurring at the exact same time, right? They exist in both, benzene rings exist in both states at the same exact time. And this idea of delocalization actually gives benzene rings increased stability compared to other unsaturated hydrocarbons. So benzene rings are pretty stable overall. And you can see this by looking at, well, we look at aromatic hydrocarbons. They actually don't undergo addition reactions that characterize most alkenes. So we look at ethylene, we brominate it, right? We halogenate it, right? We add a bromine to it. It adds, we have this product, which we've seen before. But if we try to do the same thing to a benzene ring, well, it actually just doesn't react. Right? No reaction occurs. So they are stable. Now, in terms of naming benzene rings, it's kind of business as usual with the IUPAC, but we have to think about this in just a slightly different way. So in this case, we have benzene, right? 3 double bonds, 6-member ring. We have to first name the substituent. So in this case, we have an ethyl group, or in this case, we have a butyl group, or in this case, we have a chlorine, so it's a chloro group. And then we just have to tack it onto the word benzene. So ethyl benzene is just a benzene ring with an ethyl group. A butyl benzene is a benzene ring with a butyl group, and a chlorobenzene is just a benzene group with chlorine attached to it. So it's actually kind of nice. Now, there are many types of benzene rings, and if we had lab this week, you would see these in lab, but we don't have lab this week, obviously. But some benzene rings have common names associated with them. So toluene, which is methylbenzene, phenol, hydroxybenzene, and aniline, aminobenzene, are pretty common things you'll see. So for instance, if you ever go into work in a molecular biology lab, you'll use phenol a lot. It's a pretty common chemical use. Aniline is commonly used. Sorry, sorry. The what it is dropped off my top of my head. But you can Google aniline and toluene. They're common things used. Now, when we actually are having multiple substituents here, so multiple R groups, we have a couple things we actually have to consider. Now, it depends on, so in this case, we just have two groups right now. So if they're like this, they could be like this or like this. So there's 3 distinct ways we can stick these suckers onto a benzene ring. Now, when they are in the 1 and 2 spot, they're called orthoisomers. When they're in the 1 and 3 spot, they're called meta-isomers. And when they're in the 1-4 spot, they're called para-isomers. So 1, 2, 3, 4, 1, 2, 3, and 1, 2. Right? So just as a note. Now, we can write this as one of 3 ways. So they can either have their ortho, meta, or para. So it can be ortho diethylbenzene, because I have 2 ethylene groups here, right, or ethane groups here, I should say. Or we can write that as O-diethylbenzene, or if we wanted to do the full IUPAC name, 1,2-diethylbenzene, and that's the one we know, right? If it's meta, It could be meta-diethylbenzene, M-diethylbenzene, or 1,3-diethylbenzene. And then finally, it could be para or P-diethylbenzene or 1,4-diethylbenzene. All are functionally equivalent. All would require you to draw the same exact molecule, which is nice. Now, if there are two distinct groups on the benzene ring, and they are different, you have to alphabetize them, right? So in this case, they're in the ortho position. So it'd be O or ortho, bromochlorobenzene. In this case, we have a methyl group and a fluoro group. I'm sorry, an ethyl group and a fluoro group. So E comes before eth. So it'd be ethyl, fluoro. They're in the M position, meta position, and they're on a benzene ring. So you don't have to write cyclo or anything like that. Remember, anytime you see this, right, it's benzene. So just simply a benzene ring. So you always have to alphabetize. You don't, there's no particular like, naming conventions that you have to particularly remember for this one, which is nice. Now, if one of the two substituents themselves is part of a common root, then the name of the molecule as the derivative of that monosubstituted benzene. So, for instance, if we have toluene, which we have, right? So if we go back a few slides, we had toluene, and this is what toluene looked like, or we had phenol, which is what phenol looked like. We have to essentially say, okay, this is toluene, and I'm not going to ask you to do this, but just as a note, you might see p-bromotoluene or something like that, but I'm not going to ask you to do this, but just for knowledge sake, we have to look at how this relates to that normal substituent group, right? The methyl group or the hydroxyl group here. And we have to say, okay, what position relative to this part of this group is it in? So in this case, it's in the ortho position. So it's O-chlorophenol. In this case, it's in the para position, or P-bromotoluene. So just as a note. And as with naming benzene derivatives, the number we give to the lowest possible numbers around the ring, we alphabetize them very much like we have been. And when the substituents are part of those common roots, we name the molecule as a derivative of that monosubstance, as we saw on the previous slide. And we put the common root substitute at C1, but omit the 1 from the name. So again, remember, this is phenol. It's at the 1 spot. This would have to be the 2 spot, because it has to be this substituent here has to be a lower, no, it has to be a low number too. So let's look at this. Now we have a benzene ring. We have to assign the lowest set of numbers and then alphabetize. Now if we start here as 1, 1, 2, 3, 4. If we started here, it'd be 1, 2, that doesn't work. Start here, 1, 2, 3, 4, 5, 6, that doesn't work, right? This is starting here is the lowest possible number. So 1, 2, 3, we have something at both of those positions, 1, 2, 3, 4. Thus, we have benzene, and we just have to name things. And it has to be alphabetically. So chloro comes first. So chloro is at the 4 spot. Ethyl comes next, right? CE. So that's at the 1 spot, 1 ethyl. And then the final one is propyl is at the 2 spot. So we get 4 chloro, 1 ethyl, 2 propyl, benzene. Now this naming convention you'll recognize is very similar to how we name rings in general, right? We looked at cycloalkanes. It was the exact same naming convention, right? Now the only thing different is we have benzene, right? It's just a standard ring. Now remember, if we have a common root, and again, I'm not going to test you on these common roots, but I'm just going to make mention of it since we've talked about it. We name the molecule as a derivative of that common root. In this case, it's aniline. We assign that NH group to position 1, and then we have to assign the lowest possible set of numbers. So if I went 1, 2, 3, 4, 5, 6, that would be 1, 3, 6. That's too high. 1, 2, 3, 4, 5. So 1, 2, 5. That's much better. And in this case, we have 2 chlorines. Remember, chlorine is chloro. So we have a chlorine at the 2. We have a chlorine at the 5. 2, 5. Dichloro. Remember, di being 2 chlorines. And we have aniline, so it's dichloroaniline. And again, the aniline part assumes we know that we have the benzene ring with this nitrogen group attached to it. And there are a number of other benzene derivatives. So this first one you've probably heard of, naphthalene. It's a benzene ring derivative. It's a what gives we use to kill mothballs, right? It's what mothballs are made out of. There we go. Then we have anthracene and phenanthrene. That was a tough one to say. And they have these derivatives, right? Just multiple benzene rings tacked on to one another. And there are many chemical compounds out there, and you might not realize it, that contain benzene rings. So if you've ever taken Tylenol, it has a compound named acetaminophen. That's the active ingredient in Tylenol. You can also just buy acetaminophen, say if you buy a generic form, but Tylenol is the brand name. It has a benzene ring, as you can see. Sertraline, if you've ever, sertraline is a antidepressant. It's a SSRI or something with I don't remember, something with serotonin. But you can see it has not one but two benzene rings attached to it. Its trade name is Zoloft. And then if you've ever had Lotridine, Lotridine is commonly used as a anti-allergy. There we go. It's not like Benadryl, which is diphenhydramine. It's just a different type, Lotridine. You can see it has 2 benzene rings attached to it. So again, common stuff. And there are common sunscreens. So PABA, you might have seen like ads against PABA. People don't like PABA, but P-aminobenzoic acid, this is a really common sunscreen that has a benzene ring. And then there's actually a common environmental pollutant that has, and it's also a potential carcinogen that also has 5 benzene rings, what we call benzo-A-pyrene. Just as a note, real life stuff. Yeah, so just a couple last things. Now, our aromatic compounds, our benzene rings can undergo substitution reactions primarily. Remember, substitution reactions is when one atom is replaced by another atom or a group of atoms. So in this case, we have a benzene ring with a hydrogen here. It reacts with something called XY, replacing hydrogen with the X and making HY. So remember, this is a single, right? This would be a single replacement reaction. We can also commonly see chlorination, where a chlorine atom is substitutes for a hydrogen atom in the benzene ring. So we have hydrogen atom here, reacts with chlorine gas with a catalyst of ferric chloride. You'll use this in the lab, producing chlorobenzene and hydrochloric acid. Now, for instance, the pesticide DDT, which we don't use anymore, it was banned in the the 40s or 50s, in that ballpark. It's a non-biodegradable pesticide, but you see it's got 2 benzene rings that have been chlorinated. If you guys have ever read Silent Spring by Rachel Carson, like the mother of all environmental science, she got DDT banned way back in the day. She's a pretty cool lady. And then finally, second to last, benzene rings also react with nitric acid in the presence of sulfuric acid to form nitrobenzenes. So you can see we have the benzene ring, reacts with nitrogen, HNO3, so nitric acid, in the presence of a very strong acid, sulfuric acid. Nitric acid is a relatively weak acid, as a note. And then all we do is tack on a nitrate group, NO2, and we produce water, HOH. And this is what we call nitration, adding a nitrate group to our thing. And then finally, our last thing is actually sulfa drugs. So you guys might have heard of, sulfa drugs are just a class of antibiotics. They're one of the oldest antibiotics we've ever used. They were out before penicillin. Now, they're formed by the nitration reaction. So you can see sulfanilamide here, common antimicrobial. It's been nitrated here. And you can see P-aminobenzoic acid, again, a common antimicrobial. It's been nitrated here. Whew. A lot of different words today I'm not good at saying. So that's going to be the end of today's class. I know that was a lot of stuff, but the most important things we're thinking about for today's class are namings, right? Conventions and things like that. That's kind of the gist of it. And we'll go through more of this stuff on Wednesday. So I'm going to stop recording now. If you guys have any questions, feel free to reach